Good morning, physics fans. How we doing this fine Wednesday morning? It is Wednesday, April 1st, April Fool's Day. Don't be fooling too many people in your household. I think the weatherman are trying to trick us right now. It's pretty yucky outside, but they promise us it's supposed to get nicer throughout the day. Continue. I hope everything's going well at your household. I hope everybody's feeling well. Continue your social distancing. Keep your distance away from people so we can stop spreading the virus as we go forward. Because ultimately we want to get back to where we're here in class and here in school again. So please do do your job and do your share and keep your social distancing from other people, so we can get back to some sort of normalcy. Okay, ultimately that's what we want to do. Also encourage you at some point, find a friend, FaceTime them a little bit, go have some conversations, some chit chat with your friends. Okay, I know you can sit there and message them, and that's fine, but sometimes the reason why we come to school here is to be social, and the idea of being social is getting out and talking to people, so you can FaceTime them and have some little conversation with your friends. Maybe sit down and eat lunch with them. You eat lunch, they eat lunch, you sit there and chit chat and you jabber like you do down there during cafeteria time. You can make fun of my videos, that's fine. You can make fun of them all you want. But it's our reality and what we have at this point. But please do continue to get your social distancing, and remember, keep your space between people, and we can get back to some sort of normalcy. Today we're going to talk about Archimedes' principle, and we're going to talk about buoyant forces. Once again, yesterday we talked about fluids. I will continue to try to throw 4 or 5 questions. Please do answer the 4 or 5 questions. It shows me that you're keeping up with the material. They're not going to be difficult questions at all, but it's a nice way of you just being able to continue to check up and keep in tabs with the material that we have here. The first question I have up here is, what happens when a mass is submerged in a liquid? Okay, what happens when you submerge yourself in the liquid? If you get into a bathtub, okay, and water level's at a certain level, and you get into a bathtub, what happens to the water at that level, or the water level? Well, if we take a look here, do a little demonstration. Okay, we are at, if I can hold it about straight, we're about 700 milliliters. A little bit less than 700 milliliters with respect to our fluid, maybe 650 with respect to our fluid. Here I have a mass, and if I put the mass in the water and submerge it, okay, what happens is the water level rises. I take it out, the water level goes down. I put it in, the water level rises. Take it out, the water level goes down. So what happens with the water level when we submerge an object in water is that the water level rises. So when we're talking about this, the water level will rise up. Okay? When you put yourself submerge yourself into a bathtub full of water, okay, if you fill it up to the top and then before you get in, and then you get in the bathtub, it's going to overflow. If you have a hot tub, if you get too many people sitting in a hot tub, the water level will rise and the water level will go outside the hot tub. So the water level rises when you submerge objects into water. Well, this takes us to Archimedes' principle, which should be spelled L-E. The volume displaced, the volume of fluid, the volume of displaced fluid, there we go. The volume of displaced fluid is equivalent to the volume of the object fully immersed in the fluid, or to that fraction of the volume below the surface for object partially submerged in the liquid. Once again, feel free to hit pause and go ahead and write your notes down. Okay, and that's how you slow me down a little bit. So basically, if we take a look at this, we were at 650 milliliters, and I put 500 gram mass in here, and we went up to about 750 milliliters. So the volume of this mass would be about 100 milliliters. Okay, and that's just approximate, obviously. But that will tell me what my volume of the mass is. I don't have to sit there and calculate the volume of the mass. I could just submerge it in water and measure what is my displacement of water. That's Archimedes' principle. We have an apparent weight. It's the weight of the object submerged in the fluid. The weight of an object submerged in the fluid. Now, if you have been a lifeguard, when you go to save somebody in the water, you have to go in to save them. The person is lighter in the water, or an object is going to be lighter within the water. That's what is an apparent weight. When things are submerged in a fluid, okay, when they are submerged in water or whatever fluid that you have there, the object's not going to weigh as much. Okay, it won't weigh as much because that's our apparent weight. Well, the question is why doesn't it weigh as much? And that's something that we will talk about here called the buoyant force as we go along. We have buoyancy. And that is going to be the second part of our lesson that we do today, is the buoyant force. Pressure. When we talk about pressure, pressure is the magnitude of a force exerted on a surface. And we're going to talk about a surface, and this is a surface area. Okay, it's the magnitude of the force exerted onto a surface area. That's the pressure. Okay? If I push into my head, I feel pressure from my hands because I have a surface area that I'm exerting a force on. That's the idea of pressure. And how we calculate the force is the pressure is the force that exerted over this surface area. So the surface area of my head here and the force that I'm exerting on there is the pressure that can be calculated. So pressure is force divided by surface area, or F divided by A. Once again, if I'm going too fast, push pause, that's fine. I'm just trying to speed up the download process onto YouTube. Okay, so we have the force divided by surface area, F divided by A. The units are newtons per meter squared, because we have a force divided by an area. And this is called a Pascal. Okay, named after Blaise Pascal, which was a French mathematician / scientist. Blaise Pascal. Newton per meter squared, that is called a Pascal. And this is going to be a vector quantity because we have a force, which is a vector, and we have area, which is going to be a scalar. So we have a force, a vector divided by a scalar, which is going to still give me a vector quantity. So there is a direction to the force that's being pushed on there. I'm pushing, I'm feeling pressure here, so it's making my head go that direction. See, you can sit there and chit chat how dorky my videos are, and that would be a fun thing to do. Okay, once again, looking at what we have here, we have pressure is equal to force divided by area. So if I take a look at the force, that's equal to pressure times our area. So if I have my pressure and I multiply it by the area, I can calculate what the force is, which we will use as we go down through and calculate a buoyant force, because we are going to look at the sum of the resultant force. Okay, we've all been in pools, we've jumped in pools. What happens with your ears as you swim towards the bottom of the pool? Okay, what happens to them? Well, they start to hurt a little bit, they may pop a little bit, you feel a little bit of pressure there. Well, why is that? The ears start to hurt because of the pressure of the water sitting on top of you. The weight of the water that's on top of you is giving you the pressure. Okay, that weight that's above you of all that water, if you're 10 feet below the surface of the water and you look up there, you're 10 feet below it. Well, all that water that's above you is pushing in this pressure onto your ears. And that's why you feel this pressure. It's why your ears hurt, because you're feeling all this pressure. Well, if there's pressure there, that means there's a force that's going against your ears. Okay, so that's what you're feeling when you're down underneath the water. Which leads us to the buoyant force. It's the net upward force on an immersed object. The net upward force on the immersed object. Now, if we take a look at an object, we just said that the apparent weight of an object is going to decrease because of the buoyant force. Well, if we take a look at the force diagram, okay, we have an object here. We have the force of gravity coming out here, but we're going to have this buoyant force that's going to be pushing upwards on this object. So our net weight is not going to be the same. It won't be the same. So we're going to take a look at this buoyant force. Well, we've talked about, let's take a look here, what I have hidden up here. The pressure is once again calculated by a force divided by area. So if we take a look at this diagram, we have a block here. I try to keep it simple. That's immersed in the water. Okay? So we have forces that are acting upon this block. Okay, we have gravity is pulling it down. We have a buoyant force. We have a force that's being pushed down for the water. Okay, we have force that's being pushed up here. We have different forces that are being pushed on, or that are being pushed onto this object. Okay, so the weight of the water is the force that's being exerted on top of this water. Just like when you're underneath the water in a pool, that water that's above you is the force that's being acted upon you, that you're feeling on your ears or on your face or on your ears. It's compressing. It's trying to push you together. Okay, this object is at a height. The top surface of this is at H1. The bottom surface of this is at H2. And this here is the area of the top and bottom. So to exert a force of this water on top of this object divided by the area of the top, that is the pressure. That is the pressure. And the weight of the water that's up there is the force. That is the force. So if we take a look, the mass of this water, so we're taking a look at just this water up here, all this water that's up here, that is the weight or the force that's acting upon the top surface here. So this weight of this water, not over here, but just above the surface area here, is the weight or the force that's acting upon the top part of this object. So we have the mass, the weight, force is the mass times the gravity, because once again we're just talking about weight, and how we find weight is mass times gravity divided by the area of the top. That's the pressure at the top. Now from yesterday, if we look at what we did yesterday, when we talked about density, this was mass divided by volume. So the mass of this water is equal to the density of the water and the volume of this water up above there. So the volume and the density of this water up above gives us our mass. And the volume of this water, if we take a look at just this area right here, if we take a look at the volume of this water, now remember we have a block there. we have a block that's submerged. Here is your surface area of the top. It's submerged in the water. So we have this water that's above the surface that's pushing down. And the weight of this is giving us the pressure. So that's what we have here in regards to this block. So if we take a look at the volume of this water up above here, this is equal to the area of the top. Okay, we're taking a look at this block here. The area of this top times the height of this water. Okay, all we're doing is calculating the volume of a prism. Okay, volume of a prism that we did in geometry was area times height, and that gave us our volume. So this volume of this water above this block is equal to the area of this top times the height of this top. That's our volume. So our mass then goes into our density of the water still, the area of the top times the height. Okay? The area of this top times the height gives us the mass of this water. So if I do some substitution, here's my mass of the water, here's my mass of the water. If I would sub in what we have here, we have density of water, the area of the top, and our height, which is what we have right here, times gravity divided by the area of the top. These are all being multiplied together. And once again, if I'm going too fast, feel free to pause. Okay, let yourself catch up to it. Okay, and then go again when you're ready to go again. Okay, so I'm multiplying all these and I divide by the area of the top. So now you guess what's going to happen, hopefully. I got an area of the top and I got an area of the top. They will cancel out. So we're looking at this pressure is equal to the density of the water, the height of the water, and the gravity. That is the pressure on the top of the surface. Okay? So at the level depth of H1, okay, this is the pressure that's being exerted on that top surface. Okay? Top surface, that's what we have. That's the pressure. It can be calculated by density of the water, the height of the water, and gravity. Well, if we take a look at the bottom surface here, the bottom surface, this has a height of H2. So if we take a look at the surface level at H2, we can go through the exact same thing. Then come down to the density of the water, height of the water, too, and gravity. That's our pressure that's going below, that's below the object. So we have two different heights. We have, hopefully you can see that, height 1 and height 2 are not the same. Height 1 and height 2 are not the same, so the pressure is not going to be the same at each of the height. Now, if we remember, pressure is force divided by area. And if I multiply both sides by my area, these will cancel. Our force is equal to area times our pressure. And what we've calculated here is the pressure at each of our points. The pressure at each of the points. So if we take a look at the sum of the forces in the y direction here, what we are left with is our rho GH2, okay, our rho GH2, that's the pressure, times the area. And at H1, we have rho GH1, rho water, H1G, and area of the top. So we're just multiplying both of these by our area because our force is equal to pressure times the area. this is going downwards, or the force, this is going upwards, this is going downwards. So this is going to be a negative force, this will be a positive force. And if we factor out things that are common, what do we have in common? We have these three values that are in common. We factor out the rho of the water, G, and AT. What we are left with is rho of the water, G, area of the top, and then H2 minus H1. Okay, we're left with H2 minus H1. Now, if we take a look at the area of the top, the area of this top here, and if we multiply it by H2 minus H1, okay, so we're multiplying by H2 minus H1, which is, when I take H2 minus H1, all I'm getting is that. This is your H2. My H2 takes us to the below it. H1 takes us to the top level. If I subtract that 2, what we get is we get the height of the object. This here is height of object. And if I multiply the area of the top by the height of the object, what we come up with is the volume of the object. We get the volume of the object. So the net upward force is called the buoyant force, which can be calculated by rho of the fluid, gravity, and the volume of the object, because this here is just now from over here the volume of the object. So the sum of the network, or the sum of the forces in the y direction, is your buoyant force, which is calculated by density of the fluid, gravity, and volume of the object, which is sort of unique. We have the density of the fluid here. It's dependent on density of fluid. Gravity is a constant, but the volume of the object determines what the buoyant force is. So the more volume an object has, the more buoyant force you're going to have. Okay? The smaller the object, the less volume the object has, the less of the buoyant force, which is sort of unique. This is Archimedes' principle. This is buoyant force, how we calculate and determine the buoyant force. Once again, I will suggest that you add these to your list in regards to your equation. Pressure is force divided by area. The idea of buoyant force. I would add them to your list of equations that we have been accumulating. I will post some questions about this also, so please go through and answer the questions in regards to the buoyant force for the day. Once again, that's a way of me being able to sort of keeping up with, assessing you on a daily basis, and that's why we may start adjusting this a little bit more in regards to what we're doing here. If you have any questions about this, feel free to ask. Hopefully it's fairly straightforward. It gets a little confusing when we're going through the derivation over here, but I think you should be able to handle that. That's all I have for you today. We'll do one more lesson tomorrow, and that will be the last thing we do before spring break. Once again, keep safe, keep your social distancing. Once again, I suggest FaceTiming somebody today. Talk to them a little bit, just have conversation, get some socialization going in a different direction. It's a new normal right now, so look at trying to get a different way of being able to socialize with your friends. It's important that we be able to do that. If you have any other questions, feel free to ask. Once again, please do complete the 5 questions I'm going to pose, 4 or 5 questions I'm going to pose on the notes for today. I miss you guys. I wish you were around. It's why I got into teaching, is to be able to have this interaction that I have with respect to students and respect to high school students. So we will get through this. We just have to be patient. Sometimes patience is a tough thing. But we will get through this, and we'll get back to a new normal as quickly as possible. If you have any questions, once again, feel free to post any questions or comments. Adios. Have a good day.